Hello, everyone. Welcome to the next edition of Miton Times. Today, we'll be talking about the equivariant neural networks. Feel free to ask your questions on Slido. There's the event code there on the slide, or directly on Zoom. We're going to be looking at that too. Right. So I think let's jump straight into it. Equivariant neural networks are quite a complicated topic. Equivariance in itself is a very complex mathematical concept, but luckily the development in the past years has been so that we now know that if we want to construct a equivariant neural network, we need to construct a convolutional neural network, because we know that it is not only sufficient but necessary condition for equivariance of the entire neural network. Right. Yes, go ahead. My bad. I'm going to share it. Sorry. You're absolutely right. So you should see the screen. Thank you very much. So again, this is the Slido code. I'm sorry. Right. We don't have to go over the entire complex theory. I really wanted to focus more on the intuition and the main core ideas behind constructing equivariant neural networks. I will mention some theory as well, but only briefly. So at first, this is probably what everyone expected, right? There's some definition of equivariance. I know that a lot of times it gets confused with invariance of a neural network. So let's talk about that first. So we're going to call any model, or in this case, neural network, invariant to some transformation PG if invariant, the model phi is going to be invariant to some transformation PG if it doesn't really matter if we apply the transformation or not to the input of the model. So that's the left-hand side on this plot. You can see the F input either being transformed or not with some transformation PG. And then the model is applied, and in both cases, it should give the same output. So it should not really care about the transformation that we apply. For equivariance, the situation is a little bit different. So again, we have some inputs. That's the F in and F in dagger, or not dagger, but slash. And again, we can either transform or not. But then, after we apply the model, we get the output and some different output. And what we want in the case of equivariance is that we want this output to be transformed with some other transformation PG2. And I'm going to define the proper transformation a couple of slides later. But I think the most illustrative case is in the case when, for example, the task is segmentation and the inputs are images, and PG is, for example, a rotation of this image. Then in case of equivariance, we are asking the model to rotate its output with respect to how much we rotate the input. That's the equivariance. And I have put here PG1 and PG2 on purpose. Because they can be different, and they often are. Usually, these are two representations of the same group, which I will talk about. Sorry. And so another thing that I wanted to mention at the start is, I have shown the two theorems about any equivariant neural network being convolutional. Traditional convolutional neural networks are inherently equivariant under translations. That's because of how the convolution is defined and then calculated. So if you're, for example, doing object detection and you move the object that you're looking for in the picture, the output will shift proportional to how you move it in the input, right? And equivariance is nothing new, even like without constructing equivariant neural networks. I think almost everyone has heard about feature pyramid networks that try to deal with, for example, scaling equivariance or other kinds of equivariant data, right? But yeah, so translation is something that we get for free as soon as we use Windows. And yeah, I mentioned that quite often the definition is sort of vague, and it's not really clear what is invariant, what is equivariant neural network. There's quite a bit of definitions, but I think the most widely used one comes from this paper from 1996, where equivariant neural network is defined like this. So in here, from bottom to top, we have the inputs, and the inputs can be anything, right? It can be any tensor that we can think of. And on this input space, on this feature space, we have some symmetry, which is expressed as a group. And row 0 is a representation of this group on this particular feature space. So, an example of this could be we could have a graph, for example, and we want the network to be equivariant to all the permutations. So we would find, if each, let's say, node in the graph is described by one feature of the input, then the representation would be just permutation of these features, right? Each node is described by one number, and so the representation on this space of permutations would be this. Then we would take the x0 and transform it through the first layer of the neural network. We would get x1 in both cases on the left hand and the right hand side. And in here, we can get any dimension that we can think of. We can still get one number for each node. We can increase the number, so we can have description of each node by this is 5 by 5, for example. And in this space, in this feature space, we would again find some representation of the same group, which would be the row 1, etc., etc. And so we would go through the entire network, and after each layer, we find the appropriate representation of the same group, and we're going to call the neural network equivariant. This is true for all the outputs, so even the final. Which sort of brings me here. I wanted to show the permutation more explicitly. So, for example, let's talk about the group Sn, which is permutations of n numbers and blocks. And here are some particular representations of this group, and in particular of one transformation from this group, and that's switching the first two nodes in a graph or in a set, right? And so if we, for example, take the overall output of the neural network, which could be just one number in case of classification or regression, and we would be looking for a representation of this group on this just one scalar number, it would be the first column, right? So that's the trivial representation that every group has. It's just, you map every element of the group to one, to identity. And then, everything that you want from a group still holds. I'm going to talk about it a bit later. But so this case is what the authors sometimes say when they say that the neural network is equivariant, even though it's invariant. This is exactly the case. You get one number on the output, and the representation of the underlying group that they want the network to be equivariant to is just once. So, technically, this is completely correct to say that, the neural network is equivariant, even though you mean it's invariant as a special case of this. Then, of course, if we have each node in a set or on a graph represented by one number, so, overall, we have a vector describing the features, then the particular representation of this permutation of the first two nodes is in the second picture. You can see that the colors switch in the first two rows, right? And then we can have this representation of the permutation of 1 and 2 on matrices as well, where the one of the representations that is sometimes interesting is to in the bottom right hand corner, where you can see that you apply the permutation matrix from left and from right. So you swap both columns and rows. This for example, this equivariance is sometimes interesting for models that deal with sending messages, because the first node sends message to the second node and vice versa. And so you're swapping these features, for example, in like these communication scenarios. And it really depends on the authors of the model, which equivariance they are looking for. So you can choose different representations, but this is the idea of equivariant neural network. This, of course, brings one to the question, what is the freedom? If I'm going to say that I'm going to construct an equivariant neural network, which is equivariant with respect to some particular group. Of course, for different groups, there are different representations, and these are not fixed, but they're quite well understood. So if you want to construct a neural network that is equivariant, you have a wide zoo of models that you can choose from. Because there's this sequence of theorems that I think everybody who attended some theory of groups and representations saw, and that's the Maške's theorem, which says, for finite groups, you can always find irreducible representations of the group. There's Schur's lemma, which says if you have an irreducible representation on some subspace, it's unique. You cannot find another one. And then finally, you have the Peter-Weil theorem, which says that for compact groups, you're always able to find the irreducible representations. And so people have been, taking some interesting groups one by one, and they've been classifying them, finding the representations. For most of the common groups, you can find a complete list of representations on different spaces, right? So you can choose one, and then you're going to have the equivariant neural network. There's another thing that I wanted to mention really quickly, and that's the induced representation. Sometimes, for example, in physical models where you're trying to predict some force field or some interesting physical property, which is defined in each point in space, you get these features that describe each point in the space, which have relation to the underlying spatial structure. And so sometimes you don't even have this overall freedom of choosing any representation that you want, because sometimes you get the what is called induced representation. So let's say that we have each point in space described by f of x, that's on the left hand side. So for each point in space, you get a small arrow, you get a vector that's pointing in some direction, has some size, right? And we would really like to rotate this field on the input, let's say counterclockwise. And so the first idea, that we would get would be to switch the spatial coordinates, the x, has two coordinates in it, by applying a rotation by 90 degrees, let's say. And so we would get what is in the middle, which you get by just taking each arrow and then moving it counterclockwise, but not changing the orientation. And sometimes, since you really want this field to have relation to the spatial structure, this is not the proper way to do it, right? Because you really want the arrow to mean something in the space. And so quite often you get what is called induced representation, which takes the rotation as I just described it. You can just move the arrows, but then you need to apply the induced, that's the rho of G, to the result, which rotates each arrow as well separately. That's the case in here. You can see that this sort of makes much more sense. You get the nice diagonal, the eyes top left and bottom right of the field. If you spend some time looking at these pictures, it's going to make a little bit more sense. I just wanted to mention this really briefly and not get into it because in here there's a lot of theory involved. But sometimes you know your representation is fixed for you of the group that you're interested in. Right. This was just the introduction. I wanted to define some of the things more properly. One of the things that I've been using a lot, right, are groups and their representation. So, just formally to repeat for everyone, we consider a set G to be a group if we have an associative binary operation on it, if the group has an identity element with respect to this operation, and every element of G must have an inverse element that is also, that's very basic assumptions of group. I think everybody has heard them at one point, right? And but what I think is not so obvious is the group representation that I've been using a lot. In order to define a group representation, I need to mention, what is a homomorphism between groups, and that essentially is a map that takes into account the binary operation that I have on the group, and it keeps it intact. So yeah, you can see that f of G1, G2 is just the binary operation applied to the results of f. And then group representation is exactly this homomorphism, but between the abstract idea of the group and some specific operator on some vector space V. So just being more specific, we could choose the vector space to be real vectors over real numbers, and then group representation would be a matrix that acts on these vectors. And we're looking for matrices that represent well, the abstract ideas of the groups. I'm going to show a couple of examples later on, but this is just quickly, yeah, repeat what is a group and group representation. And so, why do I want to talk about groups? Yeah, you got the idea, right? That we want to talk about symmetries in data and how to exploit them in the models. And symmetries often have characteristics of groups. So, for example, we can talk about the group which is usually labeled as E8. That's the group of all the symmetries that regular polygon with 8 sides, so octagon, has. And that's the row with the stop signs. You can see all the symmetries that that an octagon has and how they apply on the text, right? Which is, it doesn't have this symmetry. And so, yeah, in here you can see all the symmetries that are there. And for this group, we can find, for example, its representation on R2 on two-dimensional real vectors. And for this case, the corresponding matrices are at the bottom. So there's the identity element, there's reflections, rotations, all of that. So this is a very specific example of a group and its representation, right? Right. Then in order to motivate us to get into equivariance, I wanted to talk about some real-world specific examples of equivariant neural networks. I wanted to post a link to a great workshop that took place at NIPS 2020. I'm going to share the presentation later, so you can open the workshop easily. Some of the examples that I'm going to mention here are in the workshop, and some of the examples came out, since. So yeah, there's some non-trivial interaction there. One of the really nice examples of equivariant neural networks are models that are called deep sets. Yeah, you can see the paper here, and what they showed in this paper is they wanted to work with neural networks that work with sets, which by definition are unordered. And so in here, you want the model to be either invariant or equivariant to all the permutations of inputs on the set. Right. So what they showed in this paper is that if you want to construct invariant neural network that's on the left, all you have to do is process each input individually and then sum up the results. So there's weight sharing between all the neural networks that are applied to each input individually. There's the same model being applied to each member of the set, and then you do a simple addition with some weight, and like this you can approximate any invariant model. That's what the paper shows, to arbitrary precision. So that's the way you would construct something that's invariant to permutations on a set. And then if you want to construct a general equivariant neural network on a set, what they showed is on the right hand side, where the colors correspond to weight sharing. So you know, everything that's in the red is shared, everything that's in the green is shared again. And so they gave a really simple method for constructing equivariant neural networks on sets. So if we link the sets, that's the way to go. Of course, equivariance is quite frequently applied to graph neural networks. This is an example of one paper that I really like. That's the natural graph networks. And on graphs based on your domain, if it's NLP or whatever, you may be looking for some particular equivariance between graphs, and there's quite a lot of publications about this. You can find a lot of models that are equivalent in some or other sense on a graph. Right? Then a very nice application of equivariance has been this. That's what's sometimes called DNA CNNs. They take advantage of a special kind of symmetry that is present in DNA. It's called Watson-Crick model, right? So this model models DNA as a double counter helix. Each element is a pair of nucleobase. It can be C, G, A, or T. And of course, these spirals are not infinite, right? And they have two strands. And so the two symmetries that you can exploit here is the fact that you can either read each of the strands left to right or right to left. It doesn't really matter. And then there's this complementary symmetry where C only gets coupled with G and A only couples with T, I believe. And so you might want your model to be equivariant to these changes. And that's exactly what these guys did. And it improved their model significantly on all the tasks that they were doing with DNA. Then there's this paper, which I wanted to talk more about later, and really get into how the equivariance is obtained in this paper, where you can use equivariance to rotations and translations to improve your models that work with, let's say, pictures from a microscope, because it shouldn't really matter how you put your sample into the microscope. You can rotate it, you can shift it, and your model should still give the same predictions, right? And then there's more exotic uses where you can construct neural networks that are equivariant to 3D rotations. And these can be, for example, used to predict how the atmosphere is going to evolve. So you can come up with weather models and other things and really put in the equivariance into the model. And then one of the most successful uses has been in physics and chemistry, because the equivariance in both corresponds to something that you know about the system that you're modeling. So you might want your model to be equivariant to the Lorentz group, which gives rise to Maxwell equations and electromagnetic field theory. And so in these areas, you often know the group, the symmetry that you want to be equivariant to, and you can really put it into the model when you're modeling, for example, interactions of particles, or you're trying to find Hamiltonians of some complex systems, or you're trying to model, some chemical properties of molecules, because at that point, there's quite a lot of interactions between individual atoms, and yeah, the equivariance is really useful in these cases. And yeah, I mentioned the multi-part particle systems. That's usually that's described with the Clebsch-Jordan nets, where you're using the Clebsch-Jordan theory to find how the subsystems behave in a very complex system. So these are some examples of equivariance being used. I hope you found at least some of them interesting. And of course, there's a natural question of doing the equivariance differently than to what I'm talking about. And so there's been this beautiful paper about equivariance, and what these guys did was they measured how much convolutional neural networks are equivariant. If you just train them in the common way, and then you put in samples that have been transformed with some representation of some particular group. And it turns out, and it turns out that convolutional neural networks are capable of learning equivariance to quite a high degree. So if you have enough data, if you have enough weights, if you train for long enough, the neural network usually is able to a very good degree to learn the equivariance. And so there's this natural question of comparing the approaches. One of the nice things about creating equivariant models is that with the definition that I gave, each layer is equivariant. So when you're training the neural network on, let's say, augmented data or large enough data set, you only know that your entire network is equivariant. But if you want to use some embeddings from in the middle of the model, you have no idea if it is really equivariant or not. You just know that the whole model is equivariant. With the approach of constructing equivariant neural networks, you know that every layer is equivariant to what you want to do. Of course, you can ask how simple it is to implement. Convolutional neural networks have been around for quite some time. They're sometimes called the workhorses of let's say, computer vision nowadays, right? Because they're so common that almost anyone can train their own convolutional neural network. So that's really simple. And compared to that, the equivariant neural networks are more complicated. The code is a little bit more involved. But luckily, I'm going to show some implementations that everybody can use in TensorFlow and PyTorch. So that shouldn't be that much of an obstacle, but it's fair to mention that this is more complicated, of course. You can augment your data during train time or test time. This is the first row where I want to make a distinction between the two. And so if you only augment your training data, you're not really guaranteed equivariance on test data, right? Then, of course, you can augment during, predicting your test split, and then do some averaging or something like that. At that point, you're going to know that you are, equivariant. So augmentation can be used, to guarantee equivariance in test time as well. But of course, the equivariant models are always equivariant. So that's a nice advantage here. Another thing is, especially for the systems of large number of particles, the number of symmetries that you want to consider grows, a lot. It really explodes. And for these cases, you cannot really do data augmentations because you're never going to capture all of the symmetries that are in the data. So, there is a point at which the augmentation of data during training stops working, and you really need to construct your model to be equivariant. And during test time, if you only do the data augmentation during training time, that's the most efficient neural network, most efficient model that you're going to get, because you're doing nothing special during prediction, right? Compared to that, test augmentation is really hard to do because you need to augment every sample in the test split a lot and then process it. And so compared to this, equivariant models are somewhere in between. They're not quite, as simple as doing no equivariance at all, but during test time, but they are much faster and much more efficient than augmenting your data during test time. So yeah, there's the comparison to let's say some alternatives to doing equivariance. And since the time is running, I wanted to talk about a very specific example, and that's how to do rotational symmetry and how to apply this rotational symmetry to histology images. Yeah, so that's the paper I referenced earlier, right? Where what they do is they create dense steerable filter CNNs. It's quite a mouthful, and I'm going to explain every word from the title as we go. Right. What these guys did is they took a look at three very typical data sets and tasks in medical image processing. The first data set is called PCAM, and you can see some data on this slide about this data set and some samples. And what you're trying to do here is binary classification. So for each sample, you're trying to say if there is a picture of cancer or not. Really simple and straightforward. Sorry, the images are quite small, just 96 by 96 pixels each. Another task that they tackled was the crack data set. And in here, it's image segmentation. And you're trying to segment blends in some samples from the colorectal region. But from a machine learning perspective, it's a typical segmentation. And the last data set, which I think is the most famous in the medical imaging community, is the Kumar data set, where there are slices from 7 organs. And from each organ, there's like this high resolution slice, a couple of slices. And the task is to find the nuclei of each cell. So you're supposed to segment the images and draw the border around the nucleus of each cell. So these are the 3 tasks that they wanted to tackle with equivariant neural networks. They're, in my opinion, they're quite representative of what happens in medicine quite a lot, and that's that you don't have that many samples. You only get hundreds of samples, and then if you get a high quality picture, you're usually able to create slices from smaller samples from this one nice slice, but you don't get tens of thousands or hundreds of thousands of images as it would be the case for the common convolutional neural networks. And so you're worried quite a lot about overfitting, about using only a small sample of data. And this is exactly what equivariance allows you to do, because you're not asking your model to learn the equivariance from the data. You put it in there explicitly. And so usually the equivariant neural networks have about 10 times less parameters and require 10 times less number of samples to train to do the same performance. And they are less prone to overfitting because you have a low number of parameters. I have talked to some of you about this paper before, right? I believe that since then I made some new discoveries because we've been implementing this model and testing it. And so I said that I was going to explain all the words in the title. And so the first thing is the equivariance. That comes from the first paper, which introduced GCNNs. It's a beautiful paper where they achieved the equivariance by taking one filter and then rotating it. They only did it like 4 times, so they rotated 90 degrees each time, and they shared weights between these rotated filters, and then they use this as an input to the next layer, right? So it's somewhat equivalent to rotations to some degree of approximation. That's the idea here of GCNNs. Then came another paper, the second one, where this explains the steerable word in the title. They came up with a clever way to construct steerable filters. So filters that you can rotate by an arbitrary angle, not just some fixed selection of, let's say, 90 degrees each time. So these are filters that really can take on the input the angle by which you want to rotate them and then do exactly that. And then the final puzzle piece to the puzzle is the dense word in the title, and this comes from densely connected CNNs, where the idea is really simple. That's the first one that I wanted to talk about. So let's get rid of this first so that we can focus on the equivariance, right? What they did here, and they claim that it helps quite a bit, is you have, let's say convolutional blocks, and then you, after each block, you take the features and you concatenate them to the features of the next layer. And so you propagate the features, let's say, of the red of the first layer to all the consequent layers in the channel dimension. And that's it. That's what they call dense convolutional neural networks. Yeah, so again, it helps with the training. It's not a super complicated idea. And I wanted to focus on the equivariance and the idea of really going into constructing equivariant neural networks. And so the key idea in doing this comes from the GCNNs. I wanted to illustrate this on a very particular image and some filters that get applied to the image. So the input is top left, right? And then this image can either be transformed, rotated, or it can get convoluted with each filter that's in the top row. Of course, it's for illustration, right? But the first filter can be found in the image, the rest cannot. And so the output, of this convolution with all the filters, for the first filter, it would give, high output in the middle of the image. That's where the person sits, right? And so if we're thinking about this, and we want to create a neural network that's equivariant to rotations, we really need to consider an input that's rotated by 90 degrees clockwise, for example. And again, if we do the convolution with the same set of filters, which just come from rotating a single filter, this time the output would be the highest for the second filter. So in the second channel of, let's say, the layer after this. And so the key concept in creating the equivariant neural network is to do the rotation of the filters, but then consequently do a permutation on the outputs between the filters, because you can see that the first output corresponds to the second output in the bottom row. So it really should be exactly the same, right? And so in order to create an equivariant neural network, we should rotate the filters, then do the convolution with the rotated filters, and do some permutation. It should be a cyclic permutation. We're going to see how exactly this works. But this is the idea. This is the key concept. So everybody should understand this or ask the question right now. Right. Then, as I mentioned, comes the question of constructing steerable filters, which are filters that you can rotate by any angle. And this is going to be a key ingredient to creating an approximation of an equivariant neural network. We're going to take the filters, and we're not going to rotate them by 90 degrees. We're going to say, let's do 10 or 20 samples equidistant in rotations, and we're going to take the same filter, rotate it n times, and that's the approximation of the equivariance that we're going to do. So if we have enough memory, we can always expand this dimension that corresponds to just rotation of a single filter to higher n. So we can get arbitrary precision. And so there's a little bit of theory here. I don't think that I should go too much into it. And the idea is, so the first thing that we need for constructing steerable filters is to say what we mean by steerable filter. And we're going to call a filter steerable if it can be expressed as a finite sum of atomic filters for convolution. And this is advantageous because then if we want to calculate a convolution of this steerable filter, we just calculate the convolution of these atomic filters, which are fixed, predefined, and this is just some particular form that's useful to choose when we want to find some steerable filters. For example, we can choose the atomic filters to be in this factorized form, tau r, and then the rotation by angle phi. And we can choose the r's to be Gaussians. And you need the atomic filters to form a basis of the operators that you want to apply. These operators should correspond to the group symmetry that you're looking for in the representation. And so for the rotational symmetry, of course, we can choose the harmonic basis, which that's exactly the choice of phi k here. So the k is sometimes referred to as the momentum. It tells you, how many times, how many maximums and minimums you're going to have if you go through the filter and rotate. And then r gives you, the function if you go further from the center of the filter. And this is a clever way of choosing the basis of these functions. I don't think that we should stop here because I don't think it's going to be obvious just from the slides. And rather, I should show you, the atomic filters that work for the rotation equivariance. So on the horizontal axis, you get the momentum. So that tells you how many maxima and minima you hit if you, take a look at the filter while rotating. So you can see that for 0, there's 1 maximum. For 1, there's 1 maximum and minimum, etc. And it goes up. And I mentioned that the radial direction is chosen to be Gaussian. And so you increase the mean value of each Gaussian function by 1 as you go through the rows top to bottom. Bottom to top. So at 0, you get a Gaussian that has a maximum at 0. Then you get a Gaussian that has maximum at 1, at 2, at 3. It always has unit variance. And these are the atomic filters. That's the choice that you make to get something that is equivalent. This is where the group comes in. Important technical detail from the paper. You do not do this for infinity. J and K don't go to infinity. Essentially, you stop as soon as anti-aliasing takes effect. So as soon as you cannot distinguish on the grid that you're doing, in this case, it's filters 9 by 9. So as soon as you cannot distinguish maxima and minima from each other, at that point you stop increasing J and K, and that's where you cut the line. All the higher frequencies get ignored, and you get a good approximation, probably. So these are the atomic filters. That's what you fix, and a finite linear combination of these is going to create our steerable filter, something that you can rotate by an arbitrary angle. And so that's what you do. Sorry, that was on the slide even before. I chose the harmonic functions to be C functions, not R2, right? And if we want to obtain the real values of the filters, you just take the real part of this linear combination. And so the second row here tells you, how you can do a trainable filter and steer it by an arbitrary angle theta. So the psi jk, that's the atomic filters that were on the previous slides. Simple two-dimensional functions. Then the e to the minus ik theta, that's the rotation. That's how we want to steer the filter. How the theta is the angle by which we rotate the filter. And then the w, and then the w are the learned weights. In all the implementations, these are complex, and you really just take real part after you do all of these summations. And yeah, it can be shown that this is a steerable filter. It really is, some filter rotated, and you can train the weights. Right. And then in order to use this to create an equivariant neural network, you need to go layer by layer. And it turns out that the input layer needs to be a little bit different than all the subsequent layers. And there is some mathematics involved. Yeah, it's too complicated to go over here. But the idea is the input layer really is just a set of some number of steerable filters. So you get the atomic filters, and then you create n, which you choose yourself. It's the same as the number of convolutional filters of these steerable filters, and that's what you train. So that's really simple input layer, and then the next layers are a little bit more involved. Again, this is the mathematics. You can go through it if somebody has some questions about it. But the idea is after the first layer, after the input layer, and then it's through after all of those, you can consider the features to be functions on a group. And so you can calculate a group convolution instead of the common convolution where you get the same integral, but if you calculate the convolutions across some space, you are moving across entire R2 or R3, whatever. And in here, you integrate over the entire group. So you need to make some assumptions about the group. And yeah, that's the basic idea. You consider the features to be functions on the group, and then you can integrate over the entire group. With some mathematical tricks, you're really able to express it as multiplication of matrices. That's the last row here, which is really, really nice. And yeah, after you do this group convolution, which I have on the next slide in a more intuitive way, you again apply some, you add some bias and apply some nonlinearity, and that's really it. I really want to move to this slide because in here it's much more clear. So if you want to construct an equivariant neural network, you first choose the atomic basis filters. That's the first thing, right? I mentioned the 9x9 filters that are going to be steerable. So they allow for construction of rotation equivariant neural networks. Then you get the input layer. So you learn the weights in the linear combination of convolutions of these atomic filters. And so that's the image labeled as B. You get as many outputs as you have the steerable filters. So you choose, for example, 10 steerable filters. You learn 10 sets of weights for each atomic filter. So you get the column, and I mentioned that this can be considered a function on this group, right? And then the more complicated, the G convolutions are the image C, where again, you have these individual filters, but then you do the additional shift that I mentioned before is at the core of creating equivariant neural networks. So you create the steerable filter, and you steer it by some angle. Let's say you can choose to do 10 rotations to get a very good approximation of equivariance to rotations. And so you get the steerable filter, and then you create 10 copies of it, and each of these filters is rotated by 36 degrees. And you get 10 copies of this steerable filter, and between the copies, before you stack them together in the filter dimension, you do the permutation, because each rotated filter also changes. You need to do the permutation that I mentioned with the guy who was meditating as well, and that's how you arrive at an approximation of equivariant neural network that's equivariant to rotations. You get the translations for free since you're doing convolutions, right? But yeah, this is the basic idea. And then there's examples of this in the bottom row. So you do the rotation of the steerable filters, and in here is then the G convolution, and doing the sampling of the 10 steerable or each steerable filter 10 times, and you do the permutation. So you can see the kind of colors always correspond to what you do. So you rotate by some angle, and then you apply additional permutation in order to get equivariant layer. Yeah, I don't know if I explained this well enough to understand, but hopefully everyone can come back to it later on. And so these are the basic building blocks of equivariant neural networks. Each layer is going to be equivariant. And finally, I wanted to show a little bit of how these models perform. You can, of course, compare them to just convolutional neural networks when you're not doing the extra work of doing steerable filters, sampling the steerable filters. And that's for example here. So you're taking exactly the same input, and you're taking a look at the features somewhere in the middle in the network. And you rotate the input a couple of times, and you take a look how the features change. So you can see that the bottom row is the motion compensated view. So the picture is rotated back to the original position, right, after running through the model. And you can see that the standard convolutional neural network changes quite a bit as the input rotates. And then the last column is the model that I've been talking about, where you can see, especially in the stabilized view or the motion compensated view, that the features almost do not change at all. So to a much higher degree, we get something that's equivariant with respect to rotations. Then another nice image from the paper is here you can take a look at average variance of the features when you do rotation of the input image. On the left, again, is the standard convolution. On the right is the equivariant CNN. And you can see that the variance goes much closer to 0 for when the model is done equivariantly compared to just the convolutional neural networks. And the nice thing is that this model is not just nice in theory, but it actually performs really well on the 3 tasks that I mentioned. On all of them, it's labeled as dense steerable filters. CNN is the current state-of-the-art model. So they were able to beat all the predecessors. You can see the GCNNs. That's the guys who just rotated the filters 4 times. Then it's the steerable filters, and what they did, they added the dense part, so they were concatenating the features, and with that, they were able to get SOTA on Pecan, SOTA on Craig, and SOTA on Kumar, which is really nice to see. Right, and the beautiful thing about these authors is they published their code on GitHub, so everybody can download it, use it. You can even download the pre-trained models. Which is why I really like using this model as well, not just general equivariant neural networks. And that's the end of the presentation. So are there any questions? Sure.
It's quite tricky to me, and thanks, nice talk.
Thank you.
But honestly, I'm not able to answer myself. I would say a rather simple question: what is the difference between those GCNNs and steerable GCNNs, and the procedure where you augment essentially every batch? To every batch, you send all the rotations in the input, all the rotations in the output, and then contest time, you do the same and aggregate the results like every calculation.
Right. So at least based on what the authors say, when you compare the two approaches, the main difference is the artifacts of doing the transformation. When you transform either the filters or even the images, you get some artifacts of this rotation. You always need to do some, some form. You need to choose how you do the rotation. And since your image is only finite in in the sense of pixels, the rotation introduces some artifacts that the neural network then overfits to. So you really introduce something that you don't want. It's more pronounced when you rotate the filters. So if you just create one filter and then create n rotated filters instead of doing like a steerable filter that can be rotated, you introduce some artifacts to the rotation. So it could be seen on the atomic filters as well, where you get these harmonics right in the angle, and then if you do the rotation, the sampling matters. And these artifacts, they really hinder the performance of the neural network. It's going to work. It's just this works a little bit better. The difference is not huge, but it is there. You can see that's the difference in the results. The GCNN, that's just doing the rotation of the atomic filters, and this is how it compares. So the rotation of the image introduces some artifacts of doing the transformation. Right.
One more question. Are there some performance trade-offs?
Yes. You can compare it, for example, the number of parameters, and you can do it so that the number is exactly the same, which is approximately 10 times slower compared to doing just the CNN. But in this case, you're doing a little bit of an overhead when you calculate these steerable versions of the filters, when you rotate the steerable filters. So this is a little bit more intensive, but not to the point that you would really notice when you're using the model. It's a very small difference. It's approximately the same, I would say. Yeah, that's because the number of parameters is exactly the same. It can be chosen. Right. Any more questions, perhaps in Slido or in Zoom? Right. Yeah, you can always reach out to me, and if I'm able to answer, we'll talk about this more. And so the final thing that I wanted to mention is the date and time of the next times. We already know the date. It's going to be the 8th of March. And we have asked our friends from Deloitte, namely Brendan Eichner, to talk about natural language processing and open source intelligence. It's their model that they use in Deloitte. So we're going to post an announcement to the meetup page again, so that you don't miss the link, miss the date. If there are any changes, it's going to be there as well. Right. And I'm going to post the presentation under the YouTube video and to the meetup page as well, if anybody is interested. So yeah, I think that's it. And thank you for the attention. See you next time.